Hello, everyone. In this video, we're going to be going over problem 2.013 in the mass and heat in the fundamentals of mass and heat and transfer. In the fundamentals of mass and heat transfer textbook. In this problem, we are asked to calculate the thermal conductivity of air, hydrogen, and carbon dioxide, all at 300 Kelvin, assuming ideal gas behavior. And then we are asked to compare our calculated values to the values from table A4. So this is a little tricky to start with, unless you've gone through the entire textbook. But over here, uh, the main equation that you're going to need can be found on page 55, which is in chapter 2 of the textbook. Over here, we are given an equation that the coefficient of conduction is approximately 1/3 times uh, times the specific heat of the gas times the density of the gas times uh, the mean molecular speed, or the average speed that the air molecules are moving at, times the mean free path, which is the average distance between the actual molecules. So to start right off, uh, at least these first two values, uh, the specific heat and the density, these can be obtained just by like Googling, just like what is the specific heat of air, what is the density of heat of hydrogen in kilograms per cubic meter. Uh, I've already grabbed some of these values here. Air is 1.005 kilojoules per kilogram Kelvin, which is equal to 1,005 joules per kilogram Kelvin. Got a value of 14.304 kilojoules per kilogram Kelvin for the hydrogen, and carbon dioxide is 0.846 kilojoules per kilogram Kelvin. I also have the densities. Air is 1.293 kilograms per cubic meter, hydrogen is 0.089, and carbon dioxide is 1.98. These values, make sense. Hydrogen is the lightest element, so of course it have very low density, and carbon dioxide is just heavier than air, with air being a mixture of O2 and nitrogen traditionally, and carbon dioxide is two oxygens and a carbon. So, of course, that would be a heavier molecule. Now, if you look further into the page, here you'll see the equation for the mean free path, which is equal to the Boltzmann constant times the temperature, that being 300 Kelvin, over rad2 times pi d squared p. Now d squared and p are kind of out of nowhere, but the p just stands for whatever pressure. So gonna assume that this is being done all at sea level, so that's about 100 kilopascals. And the d is the diameter of the gas molecule. Now d, fortunately, can be taken from this graph right here, figure 2.8 in the textbook. It gives five different gases: hydrogen, helium, water, carbon dioxide, and air. Of course, the water is in steam at this moment. It gives the molecular mass as well as the diameter of the molecule. Hydrogen has a molecular mass of 2.016 and a diameter of 0.274. It should be mentioned that all these diameters are given in nanometers, which is times 10 to the negative 9. So hydrogen has a size of 0.274 times 10 to the negative 9 meters. So you can plug the diameters into this and get the mean free path. The mean molecular speed has to be obtained by use, can be determined from the kinetic theory of gas, which is this equation right here, where the mean velocity is equal to the square root of 3 times RT all over m. M is the molar mass of an object. You can just get this by Googling it. These are well-documented values. R is the gas constant, that being 8.314 joules per mole kilogram, joules per mole Kelvin. This is a very important value in thermodynamics and fluid dynamics, especially when dealing with ideal gases and ideal gas law. That being PV over T is equal to Rn over M, uh, something very close to that. But R is very useful in that equation. I can't remember it now off the top of my head. So also, if you scroll further down, it should be noted that technically speaking, gases have two different specific heats, one at a constant volume, another at a constant pressure. I just grabbed for these ones the main I grabbed the specific heats under constant volume, which is what I decided to do. But because there's this difference, there was a more exact equation for the coefficient of conduction provided in equation 2.12, that being K is equal to 9 gamma, where gamma is the ratio of the two specific heats, pressure over volume, minus 5 over 4 times the specific heat over pi d squared, d of course being the molecular diameter, and all that times the square root of molecular mass times the Boltzmann constant times the temperature, all over Avogadro's number times pi. Avogadro's number, right down here, being 6.022 times 10 to the 23 molecules per mole. Of course, that number is, as I just said, it's the number of molecules needed to form a mole, and a very important number to actually get atoms and elements so that they weigh a number that actually makes sense and uh not just like 10 to the minus 12 kilograms. Now that number saying 10 to the minus 9 in combination with kilograms is just meaningless to the vast majority of people. So, taking all these values, and I mainly use this equation here, using the mean free path. I got some values down here. They're all in the realm of nanometers, like 67, 194, and 43 nanometers. So for the mean free path of the CO2, it says -6. I just am bad at drawing an 8, writing an 8. For some reason, I just am sometimes. So I plugged all these values in, and I got these values down here for the conduction coefficient. Just plug it all into there. It's just a lot of arithmetic. There's no tricks to it. There's no different way of seeing it. It's just, here are the values. Here's an equation. Make it all fit. However, I also have down here all the actual coefficients from table A3. If you want to, sorry, I misspoke. Table A4. Press it here. As we can see, here are all the actual values at different temperatures. This could also be where you get like the rho and the CP and the molecular mass from. I didn't, but the values that I got was like off by like 0.002. So it's really not that much at all difference from what I got. But I must have done some of my arithmetic wrong, because pretty much for all the values that I got are about half of the actual values, which does tell me that the process that I used wasn't incorrect. I just probably messed up something very early on with the arithmetic. But, that's pretty much how this problem is done. I messed up somewhere, but, this, hopefully anyone who watches this doesn't make the same mistake that I did. Again, where that is, I don't know. As I said, this is just a lot of calculations. But, this is just the general process, and uh, very rarely is anyone going to need to determine the conduction coefficient of a gas when we can just very easily use the table, but it's always good to know how to do that. And so that's it for this problem. I hope that I explained this well. And thanks for watching.